All right, we'll get started in a little bit here. Yeah.
Exam grades by next week.
Yeah, I'm still grading it, but they'll be done by this week, yeah.
Oh, by this week?
Yeah, by this week.
Oh.
And I'll hand them back on Tuesday. All right, let's get started here. So yeah, sorry about the delay, everyone. Things just kept coming up. So great, I will finish grading exams by this week. So expect them by the end of this week. And then I have posted the second, sorry, not the second, but the next homework assignment. So this chapter is really long. So this assignment's supposed to help you kind of go through all the motions here on understanding these reactions with alkyl halides. Okay, so that will be due in 2 weeks. And the other homework, the homework that's due tonight, that's the one with SN2 reactions. That's still due tonight. So if you have any last minute questions about that, just let me know. Okay, if you need an extension, let me know as well. All right, and then the next chapter we'll talk about alcohols, ethers, and diols. I'm working on posting that homework assignment, but we're going to start talking about that today. Okay? All right, and then the quiz today, we will take it in lab. Okay, so at the end of what we talk about NMR, it will be in lab. Okay? So I also have to hand out the IR sheets too. So we'll do that after the discussion today in lab. Okay? All right. Any general questions before we resume? No? All right. So chapter 11, we kind of talked about all the different kinds of mechanisms here. How do we predict? Is it elimination, substitution, and then by what mechanism does it work? Okay? So here I'm going to write a chart here. So the title of this is likely mechanisms by which haloalkanes react with nucleophiles bases to form major organic products. All right, so here I'm going to write type of nucleophile or base. In parentheses, I'm going to put in base. Okay. All right. And then here on this column, I'm going to put type of haloalkane. All right, so our types of haloalkanes we can have. We can have CH3. All right. So in this case, L just stands for leaving group, the leaving group, okay? So we have that one. Then we have a primary haloalkane, unhindered, so that's unhindered. And then this one is hindered slightly, so this will be primary again. Two different kinds of primary. One of them has steric hindrance, one of them doesn't, okay? And then we have secondary. So these are some examples. They can be different carbon chains too, but generally speaking, this is the list. All right, and then lastly, we have tertiary. Like this. Okay, so those are all the types we can have. Now, we have classes of nucleophile we have to consider. So I'm going to write poor nucleophile. All right, and I'm going to give you an example in parentheses. So this is stuff that are relatively neutral and basically mostly oxygen nucleophiles, okay? So this will be like something like H2O. All right, so H2O would be a poor nucleophile, but still can react, okay? Now we have to talk about weakly basic. But it's not a poor nucleophile, it's a good nucleophile. Okay? Does anyone remember a good nucleophile, but it's not a very good base? Yeah, bromine, right. So you could write bromine, in this case Br minus, or, iodide. Those are two common ones for this class. Yes. Good. All right. So then we get to the strongly basic unhindered nucleophiles and then strongly basic hindered nucleophiles. Okay? So strongly basic unhindered. So example of this are negatively charged species, and they're on very basic atoms. Carbon, hydrogen, oxygen, or nitrogen. Those ones, all right? Anything else is not really considered strongly basic. So our example here is CH3, O minus. So it's charged, but it's oxygen, so it's still considered a very basic nucleophile, okay? And then the last one here we have strongly basic. But in this case, they are hindered, so they have substitution or they're branched at the reacting nucleophilic atom. Oops, sorry, I didn't mean to do that. All right, so in this case, we could use the same type of atom, O minus, except the reacting the carbon is hindered, so it will make things more complicated here. Okay, so it makes elimination even more likely. All right, so let's go down the list here. What are the mechanisms here? All right, so you have a methyl substrate. All right, will this react with water? No, it's too weak, so no reaction. Good. All right, weakly basic, good nucleophile. What mechanism do you think this one will operate through? Yes, SN2, good, SN2. All right, so here, the carbon, there's no additional carbon atom to do elimination. So in this case, all the other types of nucleophiles would proceed through SN2. Okay. So here, if we think about methyl here, okay, so think about the methyl group here, CH3, Br, right? These are considered alpha hydrogens. Okay, so no elimination possible. Because how are you going to form an alkene here? You really can't. Because if you try to form the alkene, right? Right, if you try to use a base here, where are these electrons going to go? You can't do that, right? So there's no way that happens. So no elimination possible. All right? But if you have a carbon group with hydrogens nearby, then this is possible. So these are called beta hydrogens. So to do elimination, you need a beta hydrogen to eliminate and to form an alkene. All right, so this will happen. Here's your base, boom, bam, you kick out the Br. So that's allowed. This is not allowed. So let me just re-emphasize that in red. Does not occur. Okay, so that's why these are all SN2 reactions. All right, now let's go with primary unhindered. Well, with poor nucleophile, still does not work because you can't form a carbocation, right? So that won't work. How about weakly basic? SN2. Okay. So what happens? What about strongly basic, but it's unhindered for primary? Is it still SN2 or is it E2? Yeah, still SN2, so it's still the primary product. But now, one that gets hindered, right, is going to be the opposite. You're going to favor E2. So here you got to consider a few things. Your substrate, primary, secondary, tertiary, and then also the strength and hinderedness of your nucleophile. Okay? All right, well, about primary hindered, still no reaction for primary poor nucleophiles. But now weakly basic, that will still do SN2, although it'll be slower than the unhindered substrate. Okay? But now, when we try to do a strongly basic nucleophile here, both cases, you're going to get E2 for both of them. All right? And that's because now it looks like a pseudo-secondary position because of the hinderedness, the steric bulk there. So that's why it turns to E2 for both of these. All right. All right, now we get to secondary. So this is where there's a gray area. So for a poor nucleophile, you get two situations. A slow, all right. Was it SN1 or SN2? Yeah, so SN1 only happens with poor nucleophiles. SN2 wouldn't work. The nucleophile is too weak. So you get these situations, and you get now part of E1. So with SN1, there's always some E1. You can push it to SN1 by running the reaction cold, and push it to E1 by raising the temperature. Okay? All right. Well, it's if it's weakly basic, this is where the gray area is. It's probably going to do SN2. So we're just going to say SN2 for secondary, weakly basic. And then if it's a poor nucleophile, SN1/E1. Okay? All right. But secondary, that's a tricky part now for strongly basic nucleophiles. So that will probably favor which mechanism? If it's strongly basic. Yeah, E2. So think E1. E1, pretty much poor nucleophiles. And then E2, strong nucleophiles, strongly basic. All right, now we have a tertiary position. Well, that favors what the most in this case? Yeah, SN1. And if you're not careful with temperature, you can also get competing E1 here. So that one's really fast for SN1. It's slow for secondary because the carbocation is not as stable. Okay? Now, weakly basic, well, you probably can't do SN2. So this will turn into SN1, comma, E12. All right? So this is true for both weakly basic and poor nucleophiles. And then for strongly basic and for both strongly basic nucleophiles, it will be so reactive that it's going to be E2. Okay. So use this chart to help you do the next homework assignment and predict which mechanism it is. Okay? Are there any questions? No? All right. So let's go over what makes a poor nucleophile. Let's just classify a few of them. So poor, all right, so which ones are poor nucleophiles? H2O, ROH, RCO2, H. All right. So then we get to strongly basic, unhindered. All right. So, hydroxide, sodium hydroxide, sodium medoxide, OCH3, sodium OCH2, CH3, and then sodium NH2. Okay, so these are all the kinds of bases that will be strongly basic and unhindered. Okay, and then the only really two strongly basic hindered nucleophiles you need to worry about are the sodium or potassium tert butoxide, the hindered alkoxide, and LDA. Okay, so strongly basic hindered nucleophile. All right, so sodium OCCH3, and so you could there's either the potassium one or the sodium one, so you can expect to see both. Okay, and then the other one, LDA. So I drew the structure of LDA I think last time. All right, so those are pretty much the only two types of hindered bases you need to recognize. Okay? All right. And then the last thing I'll say here is that many of the nucleophiles that we've covered, they are weakly basic and good nucleophiles like Br, I-, N3-, acetate, sulfur nucleophiles, Sr-. stuff like that. So I made a list in the start of our notes here, way like a few weeks ago. But those lists are pretty good, inclusive of the good but weakly basic nucleophiles. Weakly basic. But let me just, since I have this list there, let me just run it through them again. I minus, Br minus, Cl minus, R, CO2 minus, SH minus, SR minus, CN minus, N3 minus, and I believe those are it. So these are the examples of good nucleophiles but weakly basic. Okay, so their conjugate base is weak, relatively weak compared to the conjugate acid. Okay, so these are conjugate bases of pretty much strong or relatively strong acids. So their bases are of weak base strength. All right. So, are there any other questions on this? This is in chapter 11. So, yeah, it seems like a lot because a lot of groundwork foundations are here. So that's why it's so long. All right, and we talked about a majority of the main mechanisms that we'll see going forward. All right. So now I must forewarn you, these next few chapters, you're going to be hit with lots of reactions. And I just don't mean one or two. I mean like 5 to 10 per chapter. Okay? So it's going to be a lot. But I'll try my best to go as reasonably paced as possible. And if you have any questions, please just raise your hand or ask me. Okay? All right, so chapter 8. All right. So now we're getting to more complex reactivity here. Now we're going to talk about alcohols. So alcohols are pretty important, not just for their metabolism of alcohol, ethanol, stuff like that, but it's also present in a lot of natural products. And it's a molecule that we can use as an intermediate to get to more complex molecules. So it's very reactive. All right. So here is chapter, all right, we're jumping around here. Chapter, in your book, it is chapter 17. Alcohols. All right, so we're going to do alcohols, ethers, and diols. And I might mention phenol in this chapter too. Okay, so first we're going to cover briefly here naming. How do we name alcohols? Okay. All right. So, first let's talk about classification of alcohols. All right. So, alcohols can kind of be thought of as organic derivatives of water. All right. So, if we think about water here. Oops, sorry. Right, and alcohol is basically, looks like water, except you have some organic part of the molecule here that makes it more organic soluble, okay? So methanol is, we call it, I don't know what we call it, ambidextrous. It's like, well, not ambidextrous, but it likes to dissolve both polar molecules and non-polar molecules, okay? So classification of alcohols, just like with carbon groups, we have classifications of alcohols. All right, so this is a methyl alcohol. Methyl. All right, then we have a primary alcohol. So why do you think this one's called primary? Right, it's attached to, well, That's close. It's attached to a carbon atom that's primary. That's the reason. So I'll show you an example of what a secondary alcohol looks like. All right, secondary alcohol. The most common example is what you buy at the drugstore, maybe for disinfections, isopropyl alcohol. So this is a secondary one. So why is this one called secondary? Well, the alcohol is not bonded to two different carbon atoms, right? It's bonded to a carbon atom that is what classification? Secondary, yeah. Now, when we classify amines, it's the opposite way around. It's what you said, Elizabeth, earlier. It flips. So alcohols, the oxygen could only be bonded to one carbon and an H. So that's why we don't say a secondary alcohol is an alcohol that's bonded to two carbon atoms. Okay, and then lastly we have a tertiary alcohol. And then there's no such thing as a quaternary, because where would the OH go if there was 4 carbon atoms already bonded? All right. So are any questions on the classifications? So be able to classify alcohols based on their positions and what kind of carbon they're bonded to. Okay? All right, now let's go renaming. All right. So there's 2 ways we name this. There's a common name that has been prevalent in the history, and there's IUPAC, the naming we have been used to. So common name is alkyl, alcohol. So it's 5 carbons long, pencil alcohol. We didn't give it 6 carbons long. How would we name that? Hexyl alcohol. So you just use the alkyl group and the word alcohol at the end. Now the formal way is you take the alkane name, drop off the ANE, and write all next to it. So alkanol. All right, so let's do an example. CH3 OH methyl But here, CH3OH, if the IUPAC name, we would call it methanol, like that. Okay. So what if we do, what if we have a longer chain than that? Well, it becomes a little complicated. All right, so here are the rules for naming alcohol. So rules for IUPAC naming. All right, number 1. You must find the longest chain with the OH group. So OH is called hydroxy. Okay? So you must find the longest chain with the OH group. So if there's a longer chain without the OH group, you don't pick that one. All right? It has to be the longest chain with OH. OH is part of that chain. Okay? That's because OH now takes priority. So you're going to take this group here. All right? You're going to replace the ending. Replace ending with OL. All right? So, for example, butane, butanol. So this is where we have priority now. Alcohols are higher priority than alkanes. So that's why we don't name this as a substituent. We now change the base name. Okay? All right. So, well, if OH has priority, how do you think numbering will change? Does anyone have an idea? Yeah, so you're going to start the lowest number closest to what group? the OH, okay? So number the carbon atoms. So number the carbon chain starting at the end closer to the OH group. Good. All right. And then the rest of the nomenclature is the same. We indicate the numbering, and we also now indicate the number where the OH is. Okay. All right, and then 3 here, you're going to identify the locations of your substituents and name compounds as usual. Okay, so in this case, still alphabetical order, and the substituents that come first in alphabetical order should get you should have the lowest number possible for all substituents. Okay, so let's do some examples. So we have Br, OH. All right. So I'm going to show you 2 ways to name this. You can just pick one. The one that makes more sense to you. All right. So what position is my alcohol at? 3, 2, 1, 3. Good. So this is the 3 position. So we have, and then bromo's at the end, right? So that would get the 7. So 7 bromo. All right. Bromo. Hep. So there's 2 ways you can do this. So you write heptan because that's a heptane, right? A 7-carbon chain. But you didn't indicate where the OH is, so this is one way you can indicate it. This is now the officially accepted way, modern way of writing it. -3-all. So it's a heptane, but at the 3 position, there's an alcohol. You can write that. I don't like writing this way. I write it like this. 7 bromo, or right here, 7 bromo, 3 heptanol. All right, so you take your pick, okay? Both are equally right. But you have to write it the first way. You have to write it exactly like that, or else it won't be considered correct. Okay? All right. Are any questions about this example? No? Okay. So let's try another one. All right, now we have some stereochemistry involved. Okay, so what gets the 2 position? Or sorry, what's the OH position? 2 or 7 or 6? Good, 2. So this will be number 2. And then my chlorine would be what? 4. All right, so now let's assign R and S. All right, so if anyone has it, what's the configuration at carbon 2? Good. So 2 is S. So here we're going to put parentheses S. And then how about 4? R. Thank you. So 2S, remember 2S, 4R. Okay. Now we're going to write 4 chloro. All right. So, very similar to the ending, very similar to the first one. They're both heptanes. Okay? So, worst way do you guys like to write it? The first way or the second way? The second one? All right. So, just for these examples, I will write them both ways, but please write it the way you like. So, chloroheptan, 2-all. And yes, if it's at the 1 position, you still have to specify that too. All right? So, 4-chloroheptan, 2-all. All right. Then the next one, the other way, 2s, 4r, 4-chloro, 2-heptanol. Okay. All right. All right, how about this this one right here? So what's my parent chain? Is it 2 carbons or is it 3? No, not 2. So you want the longest chain that at least contains the OH. Yeah, it's 3. So as long as the OH is on the carbon in the chain that you number, then it's still considered the correct way. So 1, 2, 3. Okay, like that. And it doesn't matter which order you go. You could have done 1, 2, 3. It doesn't matter. So the OH is always on the second carbon. All right. So how will we name this one? All right. Well, there's 3 carbons there, right? Where's the OH? What number is the OH at? 2. All right. Do we have another substituent there? Yeah, the methyl. So let's write 2-methyl propan, 2-all. Then 2-methyl propanol. All right, that's linear alcohols in a nutshell. Are there any questions? Oh, so very similar to alkyl halides, except the ending now changes to all. Okay. All right, does anyone need me to go over any of those names or how we did that again? No? All right, so now let's just briefly go over cyclic, okay? So, remember, like you said, like in cyclic alkanes, if there's a substituent, it automatically gets the 1. Same thing for alcohols, but what gets the 1 position? Alkyl group or my OH? The OH always, okay? All right, so for cycloalkanes, don't need to specify OH's location. Or OH's location, okay? Because it's always on carbon 1, all right? Because the hydroxyl group or hydroxy group is the most, the highest priority substituent, so you don't need to locate it, okay? So, for example, let's do this one. All right, how would you name this compound? All right, I got 2-bromo. All right, so it's a cyclic structure, right? So we're going to say cyclo, what? Yeah, you got it. So you see here, we don't need to specify the number of the alcohol, and that's because it's always given the 1 position. Good. All right, let's do so let's do another one. All right. How about this one? Yeah, you got one ethyl. Yep. All right. So now there are compounds that have more than one OH. You might know one of them. You probably use it in your radiator for your car as a coolant. Okay, so like ethylene glycol, and then some other alcohols. If we convert them to other structures, they're actually found in our fats. Okay, fats that are in our bodies, fats that we consume. So they're not just these compounds we draw on paper. Okay, so now let's talk about polyols. So this is so we talked about alcohols here. Now, so let's just put these here. So this is where cyclic. Sorry, that's a weird Y. Okay, well. So here are my cyclic alcohols, my linear ones. Okay, now we're going to do diols / triols, etc. Okay, so let's do one here. Okay. So, if you have more than one OH, keep the alkane ending. All right, so let's do an example here. HO, CH2, All right, so this is the main triol that's in animal fats, or fats in general, fats, lipids, etc. Okay, so, all right, how will we number this? Well, I think there's only one way to number it, right? It's pretty symmetrical. So, what are the positions for the OH groups? Yeah, 1, 2, and 3. So, so we call this a polyol. So 1, 2, 3. Okay. Keep the alkane name. So what would the parent name be? Propane. Okay. So we call it propane, and then we indicate. Well, we don't have to indicate it here, but now we just put the ending. Okay. So if it was 2 OHs, it's DIOL, diol. But in this case, it's 3, so we use the prefix for 3, triol. So TRIOL. Okay, so that's the common name, and the common name here is glycerol or glycerin. All right, those are the most common names we know it by. All right, so that's how you would name polyols, cyclic alcohols, and linear or acyclic alcohols. Okay, are any questions on naming? So for this chapter, naming, maybe on a quiz, one question on the exam or something, but naming here, we should keep in mind how to name some things. That'll always appear on exams, okay? But Just one more time. Any more questions on naming? No? All right, let's talk about physical properties. So remember we said alkanes, nonpolar, alkyl halides, slightly polar. Now we're talking about alcohols. How do you think that compares in terms of solubility and boiling point? Let's talk first about solubility in water. Do you think alcohols are more soluble in water than alkanes or less soluble? All right, I think I heard two different answers. So you think alcohols are more soluble in water? Okay, maybe we didn't hear the solvent. Compared to water, are alkanes more soluble in water or are alcohols more soluble in water? Yeah. So remember, water and alcohols, don't they look pretty similar in terms of their structure here, but also in terms of the types of atoms bonded to the oxygen, right? So physically similar, and that's because they have hydrogen bonding, okay? So here we're going to say like water. Alcohols are polar. And capable of making hydrogen bonding interaction. So, hydrogen bonding okay, so let me show you a example. All right. So remember on our structures here, which atom has the partially negative charge? Oxygen. And this is a very polar bond. So H will have the partially positive, and water here can interact more easily or more effectively with alcohols rather than ethers. Alkanes. Okay? So we have that situation here, and then we can also draw one more interaction with the alcohol through the hydrogen of water. Like that. Like that. Okay? So don't forget that these interactions exist, because you never know. Might actually explain why these boiling points are higher for alcohols relative to alkanes, and you want to be able to show this interaction. Okay? So as a result of this, okay, solubility would increase, okay? And compared to alkanes or haloalkanes, how do you think their boiling point would change? Higher or lower? Which one's lower, the alkane or the alcohol? No, it'll be reversed. Higher, so more effective, more hydrogen bonding means higher boiling point. And that's because it takes more energy to break this interaction. Okay. So as a result of this, alcohols have higher boiling points. Okay, for example, methane's a gas, so its intermolecular forces are lower, whereas methanol is a liquid, and that's because of the hydrogen bonding between its molecules. Okay, for example, let's use methane as our example. Okay, so let's think of this as our methane molecule, and we have another methane molecule. All right, so this attractive force here, very, let me see, let's go back. Very weak forces, so very weak forces here. Okay, but if we compare a molecule of methanol, like so, okay. So that's a much stronger force because there's actually partial charges. On methane, there's really no partial charge because it's so weak. The dipoles are so weak that they only form instantaneously, so they're very easy to break. And that's why methane is a gas at room temperature. And methanol here is a liquid. So very strong bonds here, liquid. And very weak ones here, gas. So all it has to do with intermolecular forces. Okay? All right. Are any questions about boiling point? So this thing of boiling point, look for the strongest polar bonds in the molecule. So the more polar bonds, the higher the boiling point. And if there's no polarity and it's relatively nonpolar, that's going to be less lower boiling point. Okay. Are any questions on the physical properties here? Okay, well, let's now talk about acidity. All right, so with alcohols and with most of organic, you have to consider pKa, acidity, because without considering that, understanding reactivity is a lot harder, okay? So before we take a little break here, let's talk about acidity of alcohols. All right. So like water, do you really consider alcohols acidic? Or do you consider water acidic? No, right? We consider it neutral. Alcohols are pretty much the same. They're not acids or bases unless they have help, okay? Whereas strong acids, they'll just form acids directly in solution. Alcohols, though, and water, they don't do that. Okay. So let's talk about the acidity. How do we measure acidity here? So we got Ka. All right. Does this seem familiar to anyone? How do I complete this? What's Ka equal to? Yes, right. So H plus is H3O plus, right? And what's the other part here? RO minus. Good. Thank you. And here's the concentration of our initial reactant, right? ROH, or alcohol. Okay. And remember, pKa, how we get a value for pKa is the negative log. So it's like taking the pH. Is the negative log of the Ka. So this tells us in a numerical scale what's the stronger acid versus the weaker acid. Good. All right. So let's compare pKa. So the pKa of alcohols changes based on what kind of alcohol you are: primary, secondary, methyl, or tertiary. All right. So let's look at our compounds. All right. So compound H2O. So in some textbooks, people will say the pKa of water is 14, but that's not correct. You have to consider water as your reactant versus your solvent. Okay? So for our purposes, just take what I say here as the fact here. All right, secondary alcohol. Then we have tertiary. All right, so here are the values of the pKa of our alcohols. All right, 15.7 for water. Very close to water for methanol, 15.5. And then 15.9 for a primary. 17.1 for a secondary isopropyl. And then 18 for tert-butyl or tertiary one. So in this direction, we have increasing acidity of alcohols. Okay, and there's a reason why this happens. It has to do with how well something can be solvated at the conjugate base. Okay, so we'll talk. We could talk about that a little bit here. So think about this before we take a little break here. So let's compare methanol, the conjugate base of methanol. Okay, so methanol can interact with water. Okay, like so. Like so. Yes.
But the compounds that have the pKa of 15.7 and 15.5, is it intentional for them to be in that order?
Yes. So maybe let's reverse it a little bit. They're so close together, they're essentially the same. But we can rewrite it in this order. So let's just erase this number and this number. But they're so close together that they're really not that different. But we could do this one here, this one there. I just put it in that order so you can see the classification of the alcohols. But a good point. Thanks for bringing that up. Okay, so you see here, more water molecules can surround this methyl alcohol, the conjugate base. But if we now look at a situation where we have tert-butyl, okay, only some water molecules can approach and solvate this this negative charge here. So it's not going to be as soluble as surrounded by solvent, so it's less stable. So less solvation, less stable. And what do we say if something's less stable? If the conjugate is less stable, what does that mean for the acid? Weaker, right? It's less able to donate. Good. So less solvation, less stable, weaker acid. More solvation. Okay. More stable. Stronger acid. So both of them are O-, right? So the key here must be sterics, or the substitution pattern. All right, so that'll be solvation, C and pKa. Let's say we'll have a 10-minute break, and then we're going to talk about what if we put substituents nearby the acidic hydrogen. What happens to the pKa? We'll revisit that, okay? All right, let's take a little break here. All right, everyone sign in attendance. I don't know where it is. What's up? I'll give you that. I'll give you that. That's it, yeah. The frequencies, the stretches, yeah. What's up?
Okay, so we kind of have a situation.
All right.
So on Tuesdays and Thursdays, we both have physics in the morning.
Not both, like all of us.
Oh,
like,
yeah, and there's
like
others.
people
There's
there.
also like like at least like
Bunch
10
of them.
students at least in here that do.
Mm-hmm.
Her and like a bunch of students have it at this campus, and Emily and maybe a few others have it at Marysville campus. But the timings overlap. So can you talk to the dean about getting this class time changed?
What time is your class?
I'm not exactly sure. I emailed the professor, but I know it's gonna be Tuesday, Thursday morning, and then.
Yeah, isn't it
Friday,
like
Thursday,
7 till 12?
Wait, what?
Isn't it like 7 till 12 for physics, lab, and lecture?
7:30 to 12.
Yeah, we already talked about it. We moved it.
Yeah, oh, I
Yeah.
told her.
Okay.
Yeah, we moved it.
Okay.
I was kind of inconvenienced by it, but you know, we want to get transfer, right? So it'll be fine. We'll just be at, what is it, 12? So, gosh, it'll be a rough day. You're gonna have all physics, then 18B lab on Thursday, and then lecture right after.
Okay.
So it's kind of similar to your physics. Lab lecture, and then right after lab lecture.
Is it gonna start at 1, like 12:30, like?
I think the lab is 12 to 250, or something like that.
It starts at 12:30.
12 to 250, and then it's 3 to 450 is lecture.
12 to
2 to 250. The lab's 3 hours long.
12:30.
Okay, it's fine. I
So it's rough for you guys because you guys have no break, no lunch. So I don't know. Think about that.
You know, I'm not trying to make it to class every single time. You guys are gonna be fucking what can do in my class.
Andrew, are we gonna have to do this, like identify which compound?
Yeah, you won't get this many options though.
Okay.
It'll be smaller.
And then should we identify SP1 or SP, SP3, SP2? Kind of how?
Well, identify like which functional groups are present.
Okay.
Okay. So like, you know, you get to use this, so this will help you tremendously.
Yeah.
Okay, this will help you. And then you have to kind of use this information, given the spectrum, figure out what compound, out of the list of compounds, which one matches the IR.
Okay, so kind of like that, and then.
Yeah, and then you'll probably have to provide your rationale why you made your choice. So you
Okay.
can't be like, oh, it all matches. You have to be more specific than that.
Okay. Thank you so much.
How many questions are on the test?
There's only one side. So 3.
Do we need to know what you're asking?
No. Yeah, we have to explain why.
And
we're
V,
identifying
not here.
what, so you have to write
Raven's sick.
Explain if it's safe.
Maria, not
the
here.
numbers, and then identify their and the functioning groups for that, but.
Andrew, and lab or I guess you got lab?
And
Oh, man.
no, I mean like once we're all done with the activity, it won't take the 3 hours. So you guys really work, and we get it all done. We'll take the quiz, and then we'll be out of there. Okay?
Are you doing anything this weekend?
No, I have to grade a lot.
Oh man.
Do you need help?
No. Do I need
TA hours.
TAs?
He has like 6.
No, I
No,
don't.
I'm saying like 6 people volunteer.
Andrew will do it.
No. Can't do that. What are you talking about?
Can we get extra?
Right.
Just kidding.
Yeah, so those of you in physics, we're changing the schedule, but it's going to be really hard for you guys. You have like
Isn't it back
2
to
straight
back?
labs, yeah, back to back. Well, I don't know. Physics might be less demanding. I'm not sure.
The second part? It's gonna be.
No, the second physics isn't bad. The labs are more fun to do during more like.
Wait, what time are you keeping your class last time?
No, I'm just moving the Thursday schedule. So lecture is going to go from, what is it? It was supposed to start at 2. Now it starts at 3. Lecture starts at 3, and then the lab is from 12 to 3 p.m.
Wait, so we have lab first?
Lab first, then lecture. Yeah.
For exams, would it still be exam first? Or no, lab first then exam?
I don't know how I'm gonna do that. We'll figure it out.
Yeah, Logan, we're stuck.
I know, but at 7:30, she's keeping it at 7:30.
7:30?
Yeah.
It's always so early in the morning for physics, but I will say for the second physics course, because I took
1B?
crystal, I took physics 1B. It's not as bad because you do more fun stuff,
Mm-hmm.
so it's less like math and more being like, oh, we're gonna like take, magnets and very magnetic metals and just put them and see kind of like the spread of the magnetic waves and whatnot.
So it's easier than 1A? Pretty much? Or lighter than 1A?
It's more like, 1A is more like math stuff, 1B is more like, oh, stuff that you actually can apply in real life. Being like, oh, I can see how it
More
impacts
hands-on.
colors. Yeah.
Did you do Monday, Wednesday, or no?
No, I don't think it'll work out. Monday, Wednesday, yeah, I'm not. It's so we can't make like really big changes, because we have the schedule's coming out next week.
Why don't you do a night class? Or-
No.
Oh my gosh, that'd be so long.
I know.
No. Usually it's low enrollment for the night ones.
Andrew, question. You're finishing your PhD or at UC Davis.
Yeah.
I am ready to kill whoever is running the UC Davis ship insurance stuff.
Oh, why? What's wrong?
I submitted a late waiver because
Yeah.
I wasn't sure if I was going to be fully finish my thesis before fall
Oh, yeah.
started.
Yeah.
And I submitted a late waiver and I submitted before the deadline, and I haven't heard anything back from them. And every time I keep calling or reaching out to them, no one's freaking answering me.
Yeah,
And then
you're
they-
frustrated. Yeah.
But it's like
I
I
get it.
submitted a late waiver before and they responded, it was fine, but now it's like no response.
Can you like go into their office?
They have an actual office on campus?
Oh, I thought they do. No? Oh no.
I just, there's
Yeah,
like,
usually they're responsive. I'm not sure what's.
I've sent 3 emails and there's a line, there's like a website for it where you can call them. I call the direct line and it says the number does not exist anymore.
Oh, God.
So then I call the regular student
Yeah.
like student helpline, and it'll connect me, and I'll, click the link to get connected and be like, oh, like for waiver issues. Every time I've called, no matter what time of day, it's like, we're sending you directly to voicemail because there's too many people and I had to you in line. I'm like, I've called it like 8 a.m. on the dot. I'm like, how are people beating me?
Yeah. That's.
I don't know what's going on,
I don't know.
but I hate it so much.
When's the last time you called them?
Earlier today.
Oh, really? Nothing
I've called
still?
them once a day for like 2 weeks straight.
Really? Wow. There's someone else you could call.
I'm betting you there's like one person working in that office.
Can you, you can't go to like the health center, the e-messaging? They don't.
No, because it doesn't connect the ship.
Okay, that's a damn.
I should see if they have an office.
Yeah, that's frustrating. I mean, the ship thing is expensive by itself.
Yeah, right? I'm like, I'm not paying anything.
Yeah, if you're not on the, you don't have insurance, you have to pay for it.
It's like I have my own insurance, I sent them approved, but it's like they've never sent a reply on whether or not it's been approved or denied. And I'm like,
Yeah, you know what I did one time? I just went to their office, you know, the house there, it's probably just ship, whatever. I just handed it to them one time, but that's so long ago. I'm not sure if they still do that.
doesn't mention the office because they don't want people showing up.
Yeah. Form like a queue. Oh, back in there.
Then they should have sent out a mass email. But I feel like
All right. All right. Okay, so let's resume what we were just talking about. Acidity of alcohols. So more substituents around the OH group decreases the acidity based on the solvation effect. All right, there's also a few other effects we'll talk about. We talked about this a little bit in the very first chapter of this class about acid and bases. But now we can see the effect of substituents on acidity of alcohols. So we kind of saw this in, well, I asked this type of question on the first exam. I gave you like phenol, and I said, which one's more acidic, right? So think about a situation where you have an alcohol, and then you have a very electronegative atom close by. Okay, so it's kind of its neighbor. So if it's one carbon away from the OH group, this pKa still a almost 1 pKa unit lower than methanol, so 14.3. All right, so you see it goes down as we add those electron withdrawing groups or electronegative atoms, okay? Now, what if we put a lot of, so let's do this, 3 fluorine atoms on this carbon, okay? And then CH2OH. All right, so this is called trifluoroethanol. So compared to the structure on the left, what do you think the pKa, relatively speaking, higher or lower than 14.3? Lower. Because fluorine is more electronegative, right? So that will make this 12.4. almost 2 pKa units down. And remember, pKa is on the logarithm scale, so 2 orders of magnitude is 100 times fold increase in acidity. All right. Now, if we directly substitute electron withdrawing groups on around the tertiary alcohol we just saw, all of them here. So remember, if we add all carbon groups, CH3 groups, the pKa was 18. But now if you substitute it for trifluoro groups all around, the pKa is now 5.4. So it's even more acidic than almost as acidic as acetic acid, which is 4.76. So a remarkable electronic feat there. Okay, and we can compare this with the one we just drew above. So compare it to this acid right here. Or I mean this alcohol. Like that. This pKa is 18. All right, so that's a humongous increase in acidity. It might not seem like much, but this tells us that it's about 10 to the 13th times as strong as terbutanol. So that's a lot. Okay, so we can use this property of alcohols to change its reactivity. And that's the point of using alcohols in synthesis and reactions. So now let's talk about acid-base reactions. So acid... So I want everyone to get familiar that anything with an oxygen atom or a nitrogen atom, they're relatively basic. So they can act as acids or bases, namely bases here. Okay? So let's write our ethanol, CH3, CH2, OH. All right. So we try to put this with sodium hydroxide. Nothing will really happen. That's because the equilibrium here is shifted to the reactants, so it's not really going to do much. And we can see why. H2O here, its pKa is 15.7. And ethanol here is like 15.5. So let's do 15.5 or 6. Okay? And what do we know about acid-base reactions? Where does the equilibrium lie? Or what direction is equilibrium favoring? So which side has the weaker acid? The product side, right? So it doesn't go that far, right? Only slightly, and that's because the pKa difference is very small. If you increase the pKa difference by a lot, then it will favor one side more strongly. But since this difference here is only 0.2. It's so close together they'll pretty much be in equilibrium, even though the arrows don't show that. But it's more towards the right side. Good. Now let's look at. Oh wait, I actually had the value here. It's not 5. Let's change that to 9. My bad. So I was using methanol, but ethanol is a little bit different. 50.9. So this explains why it kind of moves. It favors the right just slightly, okay? But let's use that same ethanol molecule. All right, so it's 15.9. What I mean here is the pKa. Maybe I should just write that, pKa. So we don't get confused here. pKa. All right, so let's use sodium hydride. So not sodium hydride, sodium amide, NH2. All right, so this reaction actually favors the right a lot. And only a small amount of reactants are going to be unreacted, okay? And that's because NH3 here, the conjugate acid of this, the conjugate acid of NH2, that pKa is 35. So a very big difference in pKa, and so that's why it favors the products much greater, okay? So this is essentially a forward reaction. The backward reaction doesn't really compete. Oops. So here we can say slightly product favored. All right. Here we could say virtually all product. Virtually all products. So almost 100% completion. Okay? And that's because of the different pKa values. Because the pKa values, reactions go towards the higher pKa, right? The acid that has the higher pKa, because that's the weakest. All right? So it forms the weakest acid. In this case, ammonia is the weaker acid than ethanol. Yes.
For the top one, pK of 15.9.
Yes.
Is that one the weaker acid?
Yeah. So that's why. Yeah, that's the weaker acids. That's why I drew the arrow all the way to the left.
It's not reactant favored.
Yeah, so it's reactant. It's heavily reactant favored. So I just wanted to make the case that some product forms. So let's just let's just change that wording here. So slightly products. So let's say little product formation. But yes, it's more accurate to say reactant favored. Okay, thank you. Good. All right. Any other points or questions? So if the bottom arrow to the reactants is longer, that means it's more reactant favored than product. So there will be more of the reactants than products at equilibrium. Okay? And if the arrows are reversed, it'll just be vice versa. Okay. Are there any questions about that one? Okay, so see here, we can make alcohols into a base. So now they're basic. See the alkoxides? They're basic nucleophiles now. So we can convert them to nucleophiles or convert them to good leaving groups as conjugate acids, which we'll see later on. Not in this today, but probably next time. Okay? All right, so let's talk now about the amphoteric character of alcohols. Does anyone know what this term means? Amphoteric? No. I had to answer, but no. So amphoteric means it can not only act as an acid, but also as a what? Base. So acid and base, those are like mirror images of each other. So we kind of put them hand to hand. So amphoteric means acid-base character. Amphiphilic means solubility in likes water. I think amphiphilic actually means it's both soluble in water and lipophilic solvents or organic solvents. But in our case, amphoteric, that means like dual, it has dual capability, like ambidextrous. So amphoteric here means acid and base reactivity. All right, so let's list our alcohols. So we have methanol, all right, so we said one direction was acidic, right? What do you think is the basic direction? All right, so on this end, we have increasing steric hindrance around the oxygen. Okay, so if we point in this direction, what can we say about the basicity? All right, what do we say about basicity? Let me just refresh my memory here. Okay. So here we're just talking about the conjugate acid. So if there's more steric hindrance, do you think it can act effectively as a base? Probably not. That oxygen is not going to be available. So it's actually better if the methanol is the best base. So we're going to say here increasing. I'm not talking about the conjugate base. Increasing basicity and decreasing steric hindrance. Okay, so the less steric hindrance you have, the more availability the oxygen has to get close to the hydrogen. And that's because that one hydrogen is already attached to it, so it has to approach really close to get to another hydrogen. Okay, so the key thing here is that we should recognize that alcohols are both acidic and they're also basic too. They can actually react with stuff and pick up a hydrogen. All right, so that's why we wrote things like this. Remember the basicity here? So for example, if we have an alcohol, right, it can pick up a hydrogen ion in solution. Okay, and then this will be equilibrium here. And it'll form the oxonium ion. Okay, so now here, this is H2O as a leaving group. So now this molecule right here, this can be readily attacked by nucleophiles because now that OH group has been converted to water, and that's a great leaving group. Okay, so that's one way we're going to learn how to make OH leave as a leaving group in nucleophilic substitution. All right, so now we talked about all the properties. We can finally talk about how do we make these things. All right, so let's talk about synthesis. All right, synthesis. Whoops, didn't mean to do that. All right, so there's an important part of this chapter. Put star here. This is it. All right, so there's a few ways we can make alcohols. So, making alcohols from haloalkanes by acetate substitution / hydrolysis. All right, so I have my alkyl halide, cyclopentyl bromide. I can react it with sodium acetate. So sodium O. So that's my acetate. Remember, sodium has a positive charge. Oxygen has a negative charge. All right, so since this is a secondary alkyl halide, you have to heat it up. All right, so that's why we have this elevated temperature here. 80 degrees Celsius. DMF is our solvent. All right. So what would my product be? Any ideas? Well, I don't think the ring would break, so let's keep the ring intact. But what would be happening here? Yes. Yes, we're going to form a bond to acetate now. All right, now that's the substitution part. So I'm just drawing the organic product, but here I could write the byproduct, sodium bromide. You don't have to write this on exam, okay? So sodium bromide is our byproduct. Now here is a reaction. We won't talk much, but only here in this specific transformation. If you need to get an alcohol from an ester, you will use basic hydrolysis. So here's heat. So basic hydrolysis means sodium hydroxide in water. Okay? So what this does, it cleaves this bond. And what you get is sodium, cyclopentanol plus, well, you basically get this, the starting material that you started with initially back out again. So you recycled your acetate group. All right? Because there's a problem if we just use hydroxide right away. What's the other byproduct if we use hydroxide with the bromide? We don't just get substitution, right? We also get what? So there's a reason we can't do this. Why can't we just do this? Well, you will get the alcohol, but you're going to get a significant amount of what? As well. So other than SN2, what's the other mechanism that could happen? Not SN1, but E2 or E1, right? Well, I don't think it's E1 because OH here would be very concentrated. So it'll be E2 product. So you get E2 and SN2. So for synthesis, if I asked you to make this, so say I asked you to make this from this. If you do the top route, you get 100%. You'll get 10 points out of 10. If you do the bottom route, I may give you just 6 out of 10. Because here, this yield is low, okay? Because you have competition from E2. So that would result in only 60% of the points, all right? Because of the end result there. So something we'll have to consider, okay? All right, so I'm not going to, well, there's a mechanism here for this one, but I'm not going to show you it. Unless you're interested, you can come see me during office hours. Just know that if I have an ester, so that's an ester. So if I have an ester and I react it with sodium hydroxide and heat it up, you'll get an alcohol. Okay? All right, are there any questions about this transformation? All right, so there's a few other ways we can make alcohols. So let's show that let's go over that. So the first one is making them from haloalkanes. So that's number one. All right. Number two, reduction of aldehydes, ketones, and esters. All right. So the main focus for here, we're just going to focus on two of them. Aldehydes and ketones. All right. Esters. We could focus on esters. But I'll just tell you right now, these two aldehydes and ketones, that's our focus here. Esters go by different mechanisms, so that's why we usually don't cover it right here. All right. So, if we talk about reduction here, there's a specific mechanism name. So the mechanism here is called nucleophilic addition. All right, so this is for aldehydes and ketones. All right, so let's draw a generic carbonyl compound. So here's where our charges matter. All right, which atom shown is partially positive? Yeah, partial carbon. This means the oxygen is partially negative. All right, and then if we draw a resin structure, how would this resin structure look like? So there's no double bond now, right? And we have technically a bad resin structure, but carbon now will have a positive charge. Oxygen will have a negative charge. So this is why I draw resin structures. It tells us the site of where things will add. Where will electrophiles add and where will nucleophiles add. All right, so I'm going to point some arrows here. So here's my first arrow. All right, this is my nucleophilic center. All right, so that's where a nucleophile will attack from. So that's where it's nucleophilic. Electron rich means nucleophilic. All right, so if I had another nucleophile, it will add to the bottom region here. So this center right here, this is the opposite of reactivity. So this is called our electrophilic center. All right, so that's where electrophiles will add or combine with a nucleophile to form a new bond. And then the nucleophilic center, that can either be used to attack a different electrophile or to grab a proton from an acid. Okay? All right, so let's do some examples here. Okay, so here's my carbonyl group. Let's just show us what we mean here. So based on our charges we just drew, what position do you think this nucleophile will add? At the carbon or at the oxygen? At the carbon. Why? Why the carbon? Well, the nucleophile has what attached to it? A lone pair. Those are electrons, right? So would it be attracted to a positive charge or negative charge? Positive charge. And that's where the carbon is, right? So that's what we're going to do. Like that. Okay? Now, that must mean if we had an acid present, where would that add on our carbonyl right here? Through the oxygen or through the carbon? The oxygen. All right, so these arrows can actually go up here, and then one of these lone pairs can be used to grab this hydrogen. And now we have this intermediate. So this is called a tetrahedral intermediate. And this is the first step of, well, this is the product of addition, nucleophilic addition. Okay? So what we have here is our nucleophile added to the double bond. And then we protonated it with an acid to stabilize it. Okay? So what happens here is, so here's our generic reaction. Reduction has a special meaning in organic. Okay? All right, let's just go back a bit. What does reduction mean? Yeah, you gain an electron. Oh, that's a very good way of putting it. Good. Okay, and what's oxidation? Losing electrons. All right, so let's think about this carbonyl. So let's redraw the carbonyl. Okay, so, well, how do we reduce a carbonyl? Well, if anything with double or triple bonds, you can add more atoms to it, just like we demonstrated. So, reduction means you're pretty much adding more bonds to carbon and getting rid of the pi bond, okay? So, in our case, H minus is our reducing agent, okay? So, it's going to add here and get rid of that bond, okay? And put these electrons back onto the oxygen. Okay, and then the last step here, you would isolate your product. So to isolate organic substances, they have to be neutral. So we add an acid source like diluted HCl or something, and then this oxygen will pick up this hydrogen, and that will turn into your alcohol. So we have to isolate the alcohol that way. So that's my alcohol, okay? So that's called reduction. So here we can say here the hydrogen, oh look, it's negatively charged. Now it formed a bond, so it lost its negative charge. So it gave up some electrons to the carbon atom. So we say here the carbon has been reduced, all right? So carbon is reduced. And that's because it was given a pair of electrons from the hydrogen ion. So that's why it's reduced there. All right. Are there any questions about the arrows? I kind of wrote that the partial charges there so we could see that nucleophiles add at one position, and then acids or electrophiles, they add at another position. Okay. So let's talk about, like, what is H minus? Where does that come from? So there are some reducing agents we'll talk about, and then we'll end there for today, okay? So, reducing agents. So where does the H minus come from? All right. So we have sodium borohydride, so sodium BH4. So sodium borohydride is used commonly with methanol, so with protic solvents. Such as alcohols. Okay. Another one is called lithium aluminum hydride. So that might look a little weird, but the aluminum hydride, that's a counter ion. So it's actually minus charge, and lithium is plus charge. So this is a complex ion as a salt. Okay. So this is much stronger, and that has to do with the small size of lithium and aluminum's electronegativity. But it's used with ethers. So there's two ethers that we'll encounter. Diethyl ether and THF. So they look like this. So ETOH looks like this. Bird angel ding. And tetrahydrofuran is the cyclic form of this 4-carbon ether. So this is THF. Very common, very, very popular solvent. So that's THF. Tetrahydrofuran. So this 5-membered ring there, that's called furan. It's commonly encountered in, not biology, but nature. All right. So let me tell you why we don't use methanol for the second one. So protic solvents. react with LiAlH4. All right, so this is not a problem with sodium borohydride, NaBH4, because it's not as reactive. So this is so reactive that if you have any alcohol or water present, it will react okay, it will react to form your lithium salt. But you're also going to form 4 molar equivalents of hydrogen gas. And if you have oxygen or hydrogen there, it's going to explode. Okay? So that's why you got to be careful of that. I've never used LiAlH. Okay? It's very reactive. So there's even more other reactive reagents like this that open in the air, it'll just spontaneously catch on fire. Okay, so yeah, dangerous stuff. All right, so how about I just we have just a few minutes. Let me just show you one way we would see this in a reaction. Okay, so I won't go over the mechanism today, but I'll go over it next time. All right, on Tuesday. So, for example, you have 4 molecules of acetone. Sorry, not acetone. This is butanone. So, sodium borohydride. Ethanol. So, I want you to think of sodium borohydride as a source of H-. It's just donating a nucleophilic hydrogen atom. Okay? And what you get here are 4 equivalents of the alcohol. So let's say this is OH, like that. So our methyl group may be pointing away from us, and the hydrogen is going from the back. Or you might get the other enantiomer where we have COH. Ethyl. The hydrogen is coming from the front instead, and the methyl group now is situated in the back. Okay? So, when you have a pointer carbon, remember, radicals, carbocations, whenever you have something like that, or a p orbital, you're going to form a racemic mixture. So, this is a racemic mixture of enantiomers. All right. Okay. Oh, but do you think it just happens to ketones? What about aldehydes? What do you guys think? Do you think it'll happen to aldehydes as well? Not much difference between ketones and aldehydes, right? Just a carbon or a hydrogen. So aldehydes are actually more reactive, but they'll still happen. So we can have 4. Same molecule here. Aldehyde instead, though. NaBH4. Ethanol. Okay? So in this case, we will not have a racemic mixture. And why is that? What can you say about this molecule? Is it chiral? No. So you don't have a racemic mixture. All right. That'll be it for today. We'll talk about the mechanism on Tuesday. Okay? All right. That'll be it.